Ever wondered what it really takes for a CNC drilling machine to create those, perfect screw threads you rely on every day? Maybe you're facing tapping issues yourself, or maybe you're just curious about the tech.
That's a great question. It really touches on something fundamental in manufacturing, doesn't it?
Yeah.
What are the key ingredients, the absolute must-haves for making reliable internal threads with a CNC machine?
Exactly. And that's precisely what we're diving into today. We're unpacking the essential features, the core stuff a CNC drilling machine needs for tapping. We'll look at different methods and why some capabilities are just, well, non-negotiable.
Right, because it's more complex than it sounds. I mean, drilling the hole is one thing,
Yeah.
but creating a precise functional thread inside that hole, that's a whole other ballgame. It needs a level of control, of synchronization that might surprise you.
Absolutely. So our mission today for you listening is to help you really get what makes for effective, reliable CNC tapping. We'll clarify terms like rigid tapping and, even look at why something seemingly simple like coolant is so vital.
We'll cut through the jargon.
Yeah, break down the technical stuff, give you the insights you need, whether you're like prepping for a project or just feeding that curiosity. Okay, so let's start with the basics. It's not just about spinning a drill bit, right? What are the core requirements? The must-haves for a CNC machine to actually tap effectively.
You've hit the nail on the head there. Just rotating a tool, that won't cut it for threads.
Mm-hmm.
At its core, tapping effectively on a CNC machine demands incredibly precise synchronization
Synchronization. Between what?
between the spindle's rotation speed, how fast it spins, and the z-axis feed, how fast it moves down. That's often called rigid tapping capability.
Okay, widget tapping. We'll come back to that. What else?
Well, beyond that, the machine absolutely needs variable spindle speed control. You need to tweak the speed for different materials, different tap sizes.
Makes sense.
Then a robust coolant system, vital. We can definitely dig into why later on.
Okay.
And the machine needs a secure way to hold the capping tools. Often that involves an automatic tool changer, an ATC, to speed things up.
Hold on, ATC. What's that exactly? And why is it important for tapping specifically?
Ah, good question. An automatic tool changer is basically a mechanism, like a robotic arm or carousel, that lets the machine quickly swap tools automatically.
Without manual intervention.
Exactly. So it can switch from the drill bit that made the hole to the tap itself, all on its own. It significantly speeds up the whole process, especially if you're doing lots of holes.
Got it. Okay, efficiency boost. Now, back to those core features you listed, the sync, speed control, coolant, tool holding. What happens if a machine, well, if it doesn't have these things dialed in, what's the risk?
Yeah, without the right setup, you're looking at a pretty significant risk of breaking taps.
Oh, right.
And trust me, a broken tap stuck in your part, that's a major headache. It takes time to get out. You might damage the workpiece trying.
Nightmare scenario.
Totally. And that obviously leads to wasted material, maybe scrapping the whole part, unexpected cost increases. It's definitely a pitfall you want to avoid in machining.
Absolutely. Okay, so another term you mentioned earlier, or maybe it was in the prep, flex tapping. It sounds, I don't know, forgiving,
Yeah.
adaptable. What's the story there?
It is, yeah, it's definitely more forgiving in certain scenarios. Flex tapping is essentially a mechanical compensation method.
Yeah.
You'd use it mainly on older CNC machines or maybe machines where achieving that perfect electronic synchronization we talked about.
The rigid tapping sync?
Exactly, where that perfect sync just isn't really possible or reliable. If you tried to tack rigidly on a machine like that, you'd likely snap taps constantly because the feed wouldn't perfectly match the thread pitch.
Right. So how does this flex tapping work around that? What's the magic trick?
The key is a special tool holder,
Huh.
a floating tool.
Zoning.
Yeah, these holders are designed with some built-in axial compensation. That means they can move just a tiny bit in and out along the tap's axis, like they have some give. So this float lets the tap essentially follow the thread it's creating as it goes into the hole. Even if the machine's feed rate isn't perfectly spot on, the tool holder's kind of taking up the slack.
Yeah.
Yeah.
Ah, I see. So the holder itself compensates for the machine's, let's say, imprecision.
What are the main upsides of using flex tapping then? Well, like you said, adaptability is a big one. Because it doesn't demand that perfect electronic handshake, you can use it on a wider range of machines, maybe older ones, less sophisticated controls.
Okay.
It's also a bit more tolerant if your programmed feed rate is slightly off. And safety-wise, that floating action helps reduce the stress on the tap, lowering the risk of breakage, particularly in older machines or with tricky materials.
Yeah.
So yeah, versatility is a benefit.
But there have to be downsides, right? Nothing's perfect. What are the trade-offs with flex tapping?
You're absolutely right. Trade-offs exist. Because of that mechanical float, getting really precise depth control can be trickier compared to rigid tapping. Also, the tapping cycles themselves,
Mm-hmm.
generally slower with flex tapping.
Mm.
And those special floating holders, they can be more complex, sometimes a bit more expensive than your standard solid holders.
Right, that makes sense. So flipping the coin, we have rigid tapping. You said it's the modern standard. Can you give us a bit more detail? What's really going on there?
Sure, rigid tapping is basically a function built into the CNC machine's control system. The machine electronically synchronizes the spindle's rotation and the Z-axis feed rate with incredible accuracy.
To match the tap.
Exactly. The goal is a perfect match with the pitch of the specific tap you're using. This essentially eliminates the need for any compensation in the tool holder itself.
So no floating holder needed then. What kind of tooling do you use?
Correct. No float needed. Because the machine guarantees that precise synchronization, rigid tapping uses solid, non-floating tool holders. Standard stuff like ER collet chucks, or sometimes specific rigid tapping collets. It actually simplifies the tooling setup and makes a whole system stiffer, more rigid.
Okay. And what are the key features, the tech bits, that make rigid tapping work so well?
The absolute heart of it is that super precise electronic synchronization. The CNC controller manages it, and it usually relies on feedback from encoders.
Encoders, like sensors.
Exactly. Highly precise sensors that constantly tell the controller the exact rotational position of the spindle. This constant feedback loop allows that perfect sync between rotating and the Z-axis movement down into the part.
Wow, okay.
And this tight control means you get very high precision in the threads. Plus, you can usually tap much faster, higher speeds and feeds compared to flex tapping.
Now, you really emphasized before that the machine has to be capable of rigid tapping. What does that involve? What does the machine actually need?
Yes, that's crucial. It's not just software or a different holder. The CNC machine itself needs the right hardware. Things like responsive servo motors that can accelerate, decelerate, and reverse direction really quickly and accurately.
Yeah.
And those accurate encoders we just mentioned are critical. Plus, the software, the brain of the machine, the CNC control, needs to have the specific rigid tapping cycles programmed into it. It's standard on most modern machines, but definitely something to verify on older equipment.
And where does rigid tapping really make the biggest difference? What kinds of jobs or industries rely on it most?
Well, it really shines anywhere. You need both high accuracy and high efficiency. Think industries like automotive, aerospace, medical
High
components.
stakes stuff?
Exactly. They often have really tight tolerances for threads, and they need to make parts quickly and reliably, often in large volumes. That's where rigid tapping becomes the go-to. Imagine the precision needed for, say, engine parts or a surgical implant. Rigid tapping delivers that.
Okay, that gives a really clear picture of what rigid tapping is. But let's dig into the why a bit more. Assuming your machine can do it, why is rigid tapping considered so important? What are those real-world benefits for someone machining parts?
That's the key question, isn't it? While flex tapping has its place, rigid tapping, when possible, just offers these significant advantages that directly lead to better results. You get tangible improvements in accuracy, how long your tools last, overall speed, and even tooling costs.
Okay, let's break those down. You said unmatched accuracy. How does rigid tapping actually achieve that?
Well, because of that direct electronic link between the spindle turning and the axis moving, it forces the tap to cut the thread exactly according to its specified pitch, revolution after revolution.
Perfectly consistent.
Perfectly consistent. Think of it like this.
Mhm.
Flex tapping might sometimes produce a thread that's slightly stretched or compressed over its length, like a slightly uneven spring. Rigid tapping is more like a perfectly machined screw. Every single thread form is identical.
Nice analogy.
And that consistency is absolutely crucial for parts that need to assemble reliably or seal properly, like hydraulic fittings or critical aerospace fasteners.
Right. And what about tap life? You said it makes taps last longer.
Yeah, because the machine precisely coordinates the feed with the tap's pitch. It eliminates almost all of that unnecessary pushing or pulling force on the tap along its axis. Axial force, right? Right. Minimizing that force drastically reduces the stress on the tap's cutting edges. This prevents premature wear, meaning your taps last significantly longer, which of course saves you money on tooling in the long run. Less downtime changing tools too.
And efficiency always important. How does rigid tapping boost speed?
The level of control you get with rigid tapping allows you to run the spindle much faster and feed the tap much quicker than you typically could with flex tapping. It's just safer and more reliable at higher parameters.
So faster cycles.
Much faster cycle times for each hole. If you're making hundreds or thousands of parts, that time saving really adds up. It can seriously increase your machine's output and lower manufacturing costs. It's a big productivity driver.
Okay, accuracy, tool life, efficiency. And you also mentioned tooling costs. How does rigid tapping help there? I thought the machine capability might be more expensive.
The machine itself might be, initially, but the tooling for rigid tapping is often simpler and cheaper. You're using standard, solid tool holders, those ER collets we mentioned. They're generally less complex, inherently more rigid, and usually less expensive than the specialized tension, compression, or floating holders needed for flex tapping.
Ah, okay. So you save on the consumables, the holders.
Exactly. So you get better performance and potentially lower ongoing tooling costs. It's a win-win if your machine supports it.
That paints a really clear picture. Rigid tapping seems like the way to go if the machine's up to it. Now, let's switch gears slightly. Something you mentioned as vital earlier. Coolant. Does a CNC machine really need coolant for tapping? I could see someone thinking maybe it's optional, messy.
That's a fair question. People might be tempted to skip it, maybe save a bit on coolant costs or keep the machine cleaner. But the short answer, yes. A resounding yes. Using coolant during CNC tapping is almost always necessary. Highly recommended, at the very least. It plays a truly fundamental role.
Why so critical? What's it actually doing down there during the cut?
Coolant really delivers 3 key benefits all at once: lubrication, cooling, and chip flushing. Tapping generates a lot of friction and heat right where the tap meets the metal. And it makes chips, obviously, which need to get out of the way.
Okay, let's unpack those. Lubrication first. How does coolant help there?
The coolant creates this thin, slippery film between the tap's cutting edges and the workpiece material. This massively reduces friction.
So less effort needed.
Exactly. Lower torque needed to turn the tap. The cutting action becomes smoother, cleaner. It also helps prevent the material you're cutting, especially softer stuff like aluminum, from sticking or welding itself onto the tap edges.
Galling.
Right. And all of this leads to a much better surface finish on the threads themselves.
Okay, lubrication makes sense. What about cooling? Why is managing heat so important in tapping?
Well, that friction we just talked about, it generates intense heat concentrated right at the cutting zone. That heat needs to go somewhere fast.
What happens if it doesn't?
If the tap gets too hot, it can actually lose its hardness. The cutting edges soften, wear out incredibly quickly, and the tool fails prematurely. Plus, excessive heat causes things to expand both the tap and the workpiece.
Thermal expansion.
Exactly, which can mess up the accuracy of the threads you're trying to cut. Coolant acts like a heat sink, basically, carrying that heat away and keeping the temperature more stable.
Got it. And the third thing, chip flushing. That sounds particularly crucial, especially if the hole doesn't go all the way through.
Absolutely critical, especially in what we call blind holes, where there's no exit for the chips at the bottom. The flow of coolant physically washes away those little metal chips that are created.
Otherwise, they just build up.
Yeah, if they aren't flushed out effectively, they can pack really tightly into the tap's flutes, the grooves on the side. This chip packing can cause the tap to jam, bind up.
And break.
Or it can force the tap to cut oversized or damaged threads as it tries to sort of push the chips out of the way.
Yeah.
So yeah, flushing is vital.
So are there different kinds of coolants? Is one type better than another for tapping?
Yes, there are several common types, each with its own strengths and weaknesses. Probably the most common are water-soluble fluids, things like emulsions or semi-synthetics. They offer a really good balance of both cooling and lubrication.
And cost-effective, usually?
Generally, yes.
Yeah.
Very widely used. And a good tip for tapping is often to run these at a slightly richer concentration than you might for general milling, say maybe 8 to 10% oil, just to boost that lubricity.
Okay. What else?
Then you have fully synthetic fluids, mostly water, really good at cooling, tend to keep the machine very clean. Their lubrication level can vary a bit depending on the additives.
Right.
And finally, there are cutting oils or neat oils, no water mixed in. These offer superior lubrication, so they're often the choice for really tough materials, stainless steels, nickel alloys, that kind of thing. Or for form tapping, which is a different process.
But less cooling.
Generally, yes. Their heat dissipation isn't as good as water-based fluids. Trade-offs as always.
And how does the coolant actually get to the tap?
The most common way is just flood coolant. A nozzle directs a stream of coolant onto the tool and the part. Pretty simple.
Okay.
But a more effective method, especially for deep holes or blind holes where chip evacuation is tough, is through spindle coolant.
Through the spindle, how does that work?
The coolant is pumped at high pressure through internal passages inside the machine's spindle, then through the tool holder, and often through the tap itself, exiting right at the cutting edges.
Wow, right at the action.
Exactly. That high-pressure blast is fantastic for forcing chips out of the way. Really effective.
So the long and short of it is, skipping coolant when tapping is basically just asking for trouble.
Precisely. You're really rolling the dice. Neglecting coolant is a fast track to premature tool failure, poor thread quality, potentially scrapping parts. It's just not worth the risk. That relatively small investment in coolant pays huge dividends in tool life and part quality.
All right, that's crystal clear. Let's try and wrap things up. What are the main takeaways for our listener from this whole deep dive into CNC tapping?
Okay, to recap, I think the main point is that effective CNC tapping needs way more than just a spinning tool. Features like that precise spindle speed and feed synchronization, the core of rigid tapping, offer really significant wins.
Wins in what areas?
In accuracy, definitely. In making your taps last longer. And in boosting speed and efficiency. That's assuming, of course, your machine has that rigid tapping capability.
And if it doesn't?
Well, then flex tapping offers that adaptable solution, especially for older machines using those compensating holders. But rigid tapping is generally the preferred route for high-performance work today.
Got it. And the coolant?
And maybe the unsung hero.
Coolant.
It's not absolutely essential for managing the heat, managing the chips, ensuring thread quality, and stopping those tabs from breaking unexpectedly. Don't skimp on the coolant.
Excellent summary. So with all that in mind, here's maybe a final thought for you, the listener. Take a moment and think about how these features connect to your own projects, or even just your understanding of how things are made. What level of precision, what level of efficiency do different parts actually need, and how do these machine capabilities, which might seem minor, play such a huge role?
Yeah, hopefully this deep dive is giving you a bit more appreciation for what goes into making something as seemingly simple as a threaded hole. There's quite a bit of tech involved.